Mr. Ponomarenko in geophysics and geophysical methods of mineral exploration. The dissertation, to declare it begun, the title of the dissertation is Reconstruction of S-wave velocities for horizontally heterogeneous gradient layers on the basis of big guided wave data. According to the order of St. Petersburg State University, number 8122, I, Professor Petrov, head of the Department of Geophysics of St. Petersburg State University, was appointed the chairperson of this council. Allow me to introduce my colleagues, members of the Dissertation Council. Professor Tatiana Yanovskaya, Doctor of Physics and Mathematics, Professor of the Department of Geophysics, St. Petersburg State University, and Vladimir Karatonsky, Doctor of Physics and Mathematics, Associate Professor of the same department. Joining us online will be Sergei Shapiro. Can you hear us? Yes, I can hear you. Good morning. Professor Shapiro is the Professor of Geophysics at Freie Universität Berlin. According to the federal law issued on the 3rd of August 1996, number 127 on science and state research policy, St. Petersburg State University was awarded the right to award scientific degrees. The decree of St. Petersburg State University to the same effect was issued on the 1st of September 2016. The session of the Academic Council is considered legally valid if participated in by at least 2/3 of the approved composition of the Council, however, not less than 3 persons. So there are 4 members of the Council attending the session, including Professor Shapiro, who is joining us online. Now, allow me to make some brief comments about our agenda. Our session may not take more than 2 hours. The agenda is as follows. I will open the session with a report on containing an overview of the key document submittals by the defendant, which will be followed by the presentation from the defendant, questions, 2 minutes per person. I will give an overview of feedback and reviews from external reviewers, followed by reviews by members of the Dissertation Council. The defendant will take some time to reply to the reviews, and the guests will be given the opportunity to ask questions. If you wish to do so, please register, please put your names on the lists provided. Before making a presentation, before asking a question, I would like each of you to introduce oneself. The defendant will then reply to the questions asked, after which the research supervisor will make a brief comment on the defendant's performance. A 5-minute break will then be declared, during which the members of the Dissertation Council will hold a discussion on the case. After which the question about the awarding the title sought will be put to the open vote. The decision will be made about the award of the title, after which the defendant will have some time for closing comments. Before we start on our agenda, I would like you to switch off your mobile phones. The session will be recorded. There will be video and audio recording of the procedures. Simultaneous translation into English will also be provided. Let us proceed on our agenda. The dissertation by Mr. Andrey Ponomarenko. Reconstruction of S-wave velocities for horizontally heterogeneous gradient layers on the basis of big-guided wave data was accepted for defense by the learned secretary of St. Petersburg State University on the 15th of August this year. The Dissertation Council was appointed by the decree of the learned secretary on the 11th of August, 2017. I have introduced members of the Dissertation Council who are in attendance. The defendant presented the following documents. Application addressed to St. Petersburg State University Rector Professor Kropachev. A certificate of completion of postgraduate course in physics issued on the 25th of December 2011. A certificate confirming the successfully passed examinations in geophysics and geophysical methods of mineral exploration. A letter of reference from the research supervisor, Professor Kashtanov. Letter of recommendation from the work group of 13 persons, Faculty of Physics, headed by the Dean of the Faculty of Physics, and signed by myself. A list of publication comprising 7 works, including 2 publications from the Ministry of Education and Science list. 1 article in a specialist journal listed in the Web of Science system. 2 copies of the dissertation, 1 in Russian, 1 in English. All the documents comply with Clause 12, Section 3 of the procedure for the award of scientific degrees at St. Petersburg State University. All the documents are in place. Do you have any questions? After no more questions, let us proceed to the material part of the defense. The defendant will be given 15 minutes to present the key principles of his research.
Dear members of the Dissertation Council and dear guests, I would like to start my report on the research. My motivation was the interest in the possibility of using gradient velocity models of a vertically inhomogeneous medium in solving the inverse displacement problems from p-guided wave data. Well, the following the following thesis I'm trying to defend in my dissertation. P-guided waves propagate in the upper part of the section and contain information about the structure. The method of inversion of P-guided waves is used to reconstruct the transverse wave velocity profile within the framework of a multi-layer model from horizontally uniform elastic layers. The multi-layer model is characterized by a large number of parameters, and gradient models can be used to reduce it. To identify and then applications of the gradient model may also be preferable to the multi-layer model when specifying a smooth initial model for the method of complete reversal of the wave field. So I was trying to use numerical instruments to use the algorithm to achieve this goal. It was necessary to solve the following tasks: to investigate the application of the method of inversion of surface waves in vertically inhomogeneous models of the layer, including gradient models; investigate the analytical description of wave fields in gradient models of the layer; develop a set of programs and algorithms that implement the inversion of fast or P-guided waves to reconstruct the velocity profile of the longitudinal wave within the framework of gradient models, and tested on numerical simulation data. And 4, apply the developed algorithm when processing the data of the field seismic experiment in order to obtain an estimate of the velocity flow profile of the longitudinal wave of the real layer. And the simplest known models of a gradient model are the model with a linear increase in velocity with depth and the model with a linear decrease in the square of the slowness with depth, which corresponds to the following law of increasing velocity with depth. In the first case, the wave field is described in terms of Bessel functions of imaginary order, and in the second case, through the airy functions of a real argument. The second description is simpler. Therefore, as a basic gradient medium, a model was chosen with a linear decrease in the square of the slowness with depth. On the basis of the chosen base model, a single layer model was first considered, in which a layer with a linear decrease in the slowness square with depth is bounded by a free surface and a homogeneous half space. In the model of the boundary, the layer and the half space have no jumps in the parameters. The density is constant. The model is described by only 3 parameters. For the model, the dispersion equation of interference refracted waves propagating along the surface of the medium surface waves in this model was derived. The roots of the dispersion equation correspond to dispersion curves, the functional dependencies of the values of the phase velocity or horizontal wave number on the frequency. The construction and analysis of dispersion curves underlies the inversion of P-guided waves. The curves are considered by the method of numerical research for the real roots of the derived dispersion equation for some fixed model parameters for a set of frequency values from the selected frequency range. The slide shows the curves in the frequency phase velocity coordinates and also the frequency horizontal wave number in the coordinates. The parameters I assessed in terms of the minimal maximum of velocity. Before I turn to the solutions, I have to say that to solve the inverse problem of estimating the velocity structure of the medium, it is necessary to reconstruct to estimate the values of the parameters of the chosen model of the layer from the data of the wave field. In our case, from the dispersion curves of surface waves. Such an estimate is made by minimizing some residual functional. In the present paper, the discrepancy functional described in literature is chosen, which consists of the sum of the values of the left-hand side of the dispersion equation for the selected model for the medium calculated at the points of the experimental dispersion waves, namely for the frequency values Fij and phase velocity Vij on the selected grid of model parameters. Before considering examples of reversal of dispersion curves for restoring the velocity structure of an elastic layer, it is necessary to show that the dispersion curves of interference p-guided waves in the acoustic models considered can be used to describe the dispersion curves of p-guided waves in elastic models, and for the subsequent solution of the inverse problem of restoring the velocity profile longitudinal wave. Under the condition of a small ratio Vs/Vp, it is known from the literature that in a simple model from an elastic homogeneous layer on an elastic homogeneous half space, the dispersion curves of acoustic normal modes are similar to the dispersion curves of fast surface waves in a similar elastic model. The p-guided waves arrive at short times and mainly consist of multiple reflections of longitudinal waves and contain information about the velocity profile of the longitudinal wave. So the red color shows the calculated dispersion curves obtained by searching for the real roots of the dispersion equation of a single layer model. Dispersion curves coincide with the maximum of the spectrum of the seismogram, as it should be. Now consider, if we consider a similar model elastic medium, where in the profile of the longitudinal wave velocity, we have the same profile as the shear wave velocity in accordance with non-layer model. But the ratio of shear wave velocity to the value of the longitudinal wave velocity is quite small. As in the previous slide, let us now turn directly to examples of solving the inverse problem. Let us consider a model of the acoustic vertically inhomogeneous medium. The environment is modeled on the basis of the real seismic environment profile that was provided by shell. Let us try to describe the velocity profile of the medium of the framework of a single layer model. The slide shows the seismogram of the pressure wave field obtained on the surface of the layer in question, as well as its space-time spectrum. Two spectral maximums are observed in the spectrum, which can be spiked as two dispersion curves. In the work, each of the dived curves was treated separately or together. The best result was obtained using the weighted inversion of both curves, with the weight of the first curve, which varied from 0 to 1. The goal was of the paper was to illustrate that This restoration, the determination of the speech structure without inclusions and with inclusions, but with inclusions, in both cases, as the initial model, we used a model obtained by the inversion of the dispersion curves of the interference surface p-guided waves in the framework of a single layer model. This slide shows that the initial model, the reconstructed model, and their central slices, together with the central slice of the true model, are demonstrated. The results show good agreement between the true and the reconstructed model, which means that the initial model is selected suitably and proposed a single layer model may be used as the initial model for the method of handling the full wave field. Finally, we consider an example for the use of the proposed models and inversion of the dispersion curves of interference p-guided waves in the framework of such models for processing the data. In the spectral the example of using a proposed model and the inversion of dispersion curves of interference p-guided waves for processing real seismic experimental data is demonstrated in this slide. The goal was to obtain a longitudinal wave velocity profile. Real data was provided by Shell. As I said, the registration of the wave field was carried out on the terrain surface, which is characterized by a small ratio Vs/Vp. This is evidence from the seismogram that the wave field, since since p-guided waves are separated with Rayleigh waves both in the space-time domain and in the space-time spectrum. In this region, the dispersion curves of p-guided waves were derived according to the positions of the spectral maximums. The resulted curves are indicated. So the distance between different modes after preliminary qualitative analysis of the behavior of the real roots of the dispersion equation of a single layer model, the clipped curves were divided into two groups and also approximate intervals for the change of the model parameters in which a solution can be found. The selected groups of the clipped curves were designated in upper and lower modes. The curves in each group are characterized by similar angles of inclination, while in the lower modes the distance between neighboring curves is also approximately the same. After isolating the groups of curves and determining suitable intervals for the model parameters, the dispersion curves of the upper and lower models were reversed within the framework of the single layer model, as well as the joint inversion of all the curves in the framework of the more complex two-layer model, and the inversion is only the lower modes within the two-layer model. The results. On the left, the main results of the work. The use of the method of inversion of p-guided waves in the framework of a continuous models of the medium is proposed. Single-layer and two-layer velocity models are considered. The dispersion equations of the interference of p-guided waves are derived. And the models considered can be extended to a model of a near-surface acoustic waveguide with a large number of layers. Numerical simulation was performed, which showed that the acoustic velocity model can be used to describe the velocity profile of a longitudinal wave. The dissertation had a number of publications, and these publications are on the list of the Minister of Education of the Russian Federation. Any questions?
In your dissertation, you used Shell data for a particular location. What was the location? Mongolia, if I can remember it right. Okay. Any more questions? Can I ask a question? Can I ask a question? Yes, of course, certainly. I have several questions relating to the dissertation. The acoustic approximation for the solution is indeed interesting. What are its limitations in the acoustic approximation? Because at some point it should stop working, it should be ineffective. It is so, but as far as numerical boundaries are concerned, we didn't study that. We did identify that the method was effective for small ratio, but no numerical boundaries, no numerical limits was set. Yes, but the conditions are necessary. What does it mean, small ratio, in your case? The key point is that the wave field must be effective to separate the P waves and Rayleigh waves in the temporary and spectral domains. It was a very interesting example with inclusions, with increments that you used. What was the size of increments compared with long waves? That's an excellent question, but I don't know how to respond to it correctly, how to answer it correctly, because for the inversion method, you use a number of sources and a number of frequencies for inversion to be able to illustrate the homogeneity principle. So your solution embraced the whole of the wave field. Yes, my part of the solution was to build the initial model for the wave field inversion, because this was one of the key principles of the method. So what you are showing on picture 3.13b in your dissertation is the outcomes, is the result for the whole of the wave field. Yes. Any more questions? Sergey, we are passing on to the discussion component of our session, and you will have plenty of opportunities to discuss the good points, the strong points, as well as the drawbacks of the dissertation. If there are no more questions, let us proceed on our agenda and provide an overview of the reports on the dissertation, external reports on the dissertation. There are two. One is from the Doctor of Mathematics, leading researcher of the Institute for Wave Processes, Oleg Motygin. His opinion contains several critical remarks. It is pointed out that the several important remarks. The originality of the method is based on the use of the acoustic model. And this is an approach that is partly advantageous and partly it has its own disadvantages. And Sergey's question was consistent with this. Another critical remark is that the defendant fails to provide enough details on the numerical methods, such as the methods that is used to identify the roots of the dispersion equation. These should be based on heuristics and experimental conclusions. Possibly this method ought to have been automated. and some algorithm for stabilizing the minimal positions ought to be formulated. Would you like to respond to these questions? Yes, I agree with these comments that this procedure can be automated. The algorithm is semi-automated as it is, but to be able to use it for arbitrary data, you need to automate it, and this is something that obviously deserves our attention in the future. I accept that. And the second review came from Doctor of Physics and Mathematics, leading researcher of St. Petersburg Department of the Institute of Mathematics, named after Steklov, Professor Alexei Kiselov. The review is a positive one, and there are no critical comments contained there. So the review is published on the university website. All the reviews have been duly published on St. Petersburg State University's official webpage and are available for public viewing. Let us pass on to the comments from members of the dissertation councils, the members of the dissertation councils present here. And may I give the floor to Professor Yanovska, one of the key researchers in this field. I won't present all of my review, but I want to comment that the work is practically relevant and theoretically relevant because seismic exploration requires good knowledge of the top part of the section. Including S-wave and P-wave velocities. As far as P-wave velocity is concerned, the author suggests a good method to determine that. The method is effective, so the work is important and highly relevant. I would like to focus on some critical comments. The first being, the first of them is related to Sergei's question. Namely, to what extent is this method applicable? And what are the values, what are the P-wave values that make this method workable? You probably should have defined the behavior of complex roots if we increase the speed of the S wave. And we need to understand how the dispersion equation root behaves in this situation. So this is one of the key errors in your estimates of P-wave and S-wave velocities. And this is something that you have failed to do so far, but probably should have done. However, this may be subject for further research. Another critical comment is that I somehow don't understand why the work mentions the approximation requiring a large number of parameters, when in fact your set of parameters is very limited in delimiting the gradient layer, because the dependence that you are using here is not realistic. Because it turns out that the velocity gradient increases with depth, which isn't true. The reverse is true. So approximation with 2 or 3 gradient layers is hardly feasible. You don't have to use a large number of parameters in resolving inversion problems. However, some values ought to be set. You need to approximate linear velocities and then the resulting linear velocity ought to be approximated step by step. In layers with constant velocities, a very well-known Thomson-Gaskell method can be used, which is applied in all problems related to surface wave inversion. These are my main critical comments. However, they are of minor nature because the dissertation is indeed scientifically very advanced and breaks some ground for further research. Mr. Ponomarenko, would you like to answer now? Yes. As for the second comment, this layer profile is highly prevalent in oceanic acoustics. However, as a subject of this research, within the framework of this dissertation, it was used because it was more simple compared with other gradient layers. So hence the dependence of velocity on the depth. Several studies have been carried out using different sets of data, which have demonstrated that for some cases this method of approximation is applicable. The key goal of this method is to obtain smooth approximation of the layer structure and use it for the complete wave field inversion. As far as the problem for the initial model of the wave field inversion is concerned, if there is an opportunity to get a smooth model, it's a good thing. It's an advantage. This was my key idea, and this idea was implemented. Important findings have been obtained for several cases, and of course I value your comments, your critical comments. I appreciate them and will try to use them in my further research activities. Thank you. I now give the floor to the next member of our academic council. Sergey, you now can fully articulate your opinion on the dissertation. Thank you very much. I think that I'm not going to familiarize you with the whole of my review, which is duly published on the university website. There are some critical comments. However, the author is aware of these. In a nutshell, the work is indeed very interesting and highly relevant. I wholly agree with Tatiana in this respect, because the problem covered in the dissertation is of high importance to mineral exploration and to seismic engineering. One interesting fact is that neosurface, as a part of geophysics, as represented in the European Geophysical Society, is growing. However, exploration geophysics or seismic exploration is stagnating at the moment. So big guided waves in the top part of the section are a captivating problem. Some of the models studied by Andrey are of high promise to industry. Shell has given us a lot of interesting examples on this. I like the dissertation. It is succinct, it's concentrated, the method is interesting, and the work is indeed very well structured. My comments are of minor nature. They do not contain any important limitations to the scientific value of the dissertation. My questions point to the same problems as Tatiana described here a few minutes ago. I also would like to point out that the method to resolve the inverse problem is indeed interesting. It involves construction of the inversion equation and attempts to find the layer parameters so that the equation is zeroed, nullified. It's an interesting method. However, to be able to use it, I would like to have some analytical definition of the dispersion equation. What happens if there are many parameters to the same layer, or even 4 to 6 layers? What do we have to do? Do we formulate the analytical dispersion equation first? In my work, I have formulated dispersion equations for single layer and 2-layer examples. If you extend this model to cover more layers, you should use something similar to the Thomson-Haskell method, where the determinant can be defined in the matrix form, using the matrix approach. So your dispersion equation may be present in the non-evident, non-apparent form, using the Thomson-Haskell propagator. Yes, that's correct. However, in this dissertation, I limited myself to analytical approximations for simple models. Okay. And as a critical comment, that I would like to review here is the usage of the weighted functional. You use it with different effect for functional data and for numerical data. Yes, this is what happened in as I was carrying out the study, because when I was processing the result of the numerical experiment, I managed to select the weighted functions fitting the result. And this was consistent with the findings of our analysis of the dispersion equation railroads. In reality, we got good results without weighted functions. I don't rule out the situation that if we had to use weighted functions consistently, we would have obtained better data, but this would have been more complex and would have taken longer time. The time costs would have been more significant. How do you select weights? What is the principle that you follow? The principle was based on the data of for numerical modeling. The model was fairly clear. I picked two dispersion curves, clipped two dispersion curves. The preliminary analysis of dispersion curves shows that the weight for the second dispersion curve ought to be larger, and for the first it should be smaller, lower. So the right part of the dispersion equation is larger for the first dispersion curve. It's a technical method, it's a technical approach. that required using lower weights for the first curves than for the second one. Thank you. And then I would like to give the floor to Peter Karatonsky.
And dear ladies and gentlemen, the work is very interesting. The models are substantiated. The work is very interesting and very good work, good quality work, both in applied sense as well. The comments, critical comments, are very similar to what we've just heard, but just a couple of questions. Well, not very good delineation of the applicability, especially of the acoustic approximation. This was in one of the comments already. And the second one, there should be some comparison, but in terms of different functionals. Andrey Valerьevich said that there's some approaches, different approaches used, but for different functionals, different results can be obtained. So these are two comments that I would like to make, but it doesn't really affect the quality of the dissertation and my appreciation of it, and so, yeah, very well done. On my part, I would like to say that yes, I would have to compare two functionals, but I did that, but not in very explicit form. So in my future research, I am going to do it. Thank you very much. So I would like to read out my review. I like the work, and a good description is provided of the existing situation, and after that a direct objective is solved concerning the gradient, and then the reverse problem is solved, and after that everything is compared with empirical data, experimental data. This is a classical approach, the direct problem, inverse problem, and the data, and so there are no objections to that. And I was very happy to see that the comparison with the experimental results has very good agreement, and to have such a good result is very worthy. And the comments are about the same, that you have to the acoustics problem and the simple gradients. So therefore, and so I would like to formulate. Would you can you present a separate the acoustic, the dispersion model, dispersion equations, and the roots of dispersion models are equations, and area functions. Would you like to say something? I would like to say that we have to write an elastic layer, my equation, and I haven't done that, and I can only say that that in my future work I will do that. And that would give us applicability, and would be very good to have whether we can do apply this in this case or not. And in terms of the gradient, in gel seismology, there's a spherical geometry, but there's an equation that people spend a lot of time for what equations, for what gradients there is an analytical solution. Have you tried with your plane geometry to arrive such a gradient? maybe with geometrical functions. Well, we can make up one like this, but there are some classes of gradients for which simple solutions are available. So one of them is the model, the layer model that I use, and I've used it because the solution looked to me the simplest of all the available ones, and so, well, in principle, then it would have been useful to look at such things for different other layers. So, on the whole, I liked the work, I enjoyed the work, and I would vote in favor of this work. So I would like to turn to the discussion on the floor, and anyone would like to ask a question or make a comments among those present. Anyone willing to do that? Well, a lot of things have been said, so if there are no questions, then I would like to turn to the next item on the agenda. Would you like to say anything as a final remark to respond to the comments? Well, you've answered. I would like to say that I agree with all the comments. They're very constructive and very useful, and I would like to use them in my future work. Thank you very much. Thank you. So, if so, the next item on the agenda is the short statement by Research Supervisor Boris Markovich. Please take the floor. The Research Supervisor, Professor of Physics and Mathematics at the Department of the Physics of the Earth, Kashtanov Boris Markovich, please. Andrey joined our laboratory in the third year of his studies, and since then he's got a grounding in theory, but also with modeling issues of wave fields and real observations. So he demonstrated initiative and very detail attentive. He is very meticulous, very perfectionist, and this is very appealing. And what the applicability, as far as the applicability issue, he took a manual method. While it's working, they're using the same thing here. You know, don't drop what is working. And so I wish him productive work in the future. Thank you very much. Any questions to the research supervisor? No questions? Okay then. So I cannot hear. Any answer? That's okay. Well, there's a list of people registered. Okay. Alexander Dmitry Vladimirovich, would you like to say anything? Alexander Dmitry Vladimirovich, candidate of physics and mathematics, senior researcher at our department. The questions are the same and have been voiced. So I would like, I don't want to extend this discussion. Thank you very much. And Trajan is also on the list. Vladimir Nikolaevich, please. And I hope that your statement, your presentation will be more substantive. And dear members of the Dissertation Council, dear colleagues, I'd like to say a few words about Andrey as a very good student, a very Boris Markham is very meticulous, but I would like to add very, very interesting, very top quality postgraduate student, because he presented his results in different conferences, because all the information has been in this dissertation has been approved by the academic community, by the academic geophysics and popular European trend in geophysics as the top layer investigations, and therefore I think that Andrey is as a researcher, top-level researcher with a good mathematical background, with a good vision of the physical process that take place inside our planet, in the narrow layer, in the top layer in this case, but this is a very important research avenue in the seismic exploration, when in exploration, oil exploration, because the top crust you can have the accuracy of the layer description. And this plays an important role, as Sergei Alexandrovich pointed out, in geophysical engineering. And why these issues are more relevant in Europe? Because of the environmental problems, because they can be resolved through using the top layer investigation, and these new methods that are now investigated, and physicists and geophysicists and mathematics are proposing now are very important and very necessary for to solve these pressing problems. And so this work is very well written. I read it very attentively, and I think that Andrey deserves the third degree of Candidate of Sciences of Physics and Mathematics. Thank you very much. Anyone else willing to present?
Sergei, do you have any further comments? If not, let us put the question to the vote. Let us take the question to the vote. I now would like to announce a 5-minute pause, a 5-minute break for discussion. Please switch off the broadcasting, and I would like our guests, I would like our visitors to leave the auditorium for 5 minutes.
Ну так хорошо.
Так, пожалуйста, садитесь.
Please be seated. The session is resumed. Can you please switch on the broadcasting? Let us take the question to the vote. Let me remind you that the decision of the Dissertation Council on the award of degrees is considered in favor if voted for by not less than a half, but at least 3 members of the Dissertation Council, according to the decree on the award of scientific degrees at St. Petersburg State University. Professor Yanovska, what is your opinion on the matter? I am convinced that the defendant deserves the academic degree sought. Sergey, your opinion? I agree. I vote in favor for the award of the degree. Your answer is yes. Yes. Peter? I am convinced that the defendant merits the academic degree sought. I also think this is a good dissertation and the defendant deserves the degree of the candidate of science and mathematics, physics and mathematics. Esteemed colleagues, esteemed visitors, I now declare that the 4 members of the Dissertation Council present voted unanimously in favor. None of them abstained from vote. The decision to award the 3rd degree in physics and geophysics to Mr. Ponomarenko is taken unanimously. Congratulations. Thank you. Alexei, you now have the floor for a concluding statement. I'm immensely grateful to you all. It's a great honor to be awarded this degree. I would like to thank my research supervisor, Boris Kashtanov, and also to Vladimir Troyanov, to members of the Geophysics Department for their support, for their assistance, for the knowledge that they have so generously shared when I was taking my bachelor's program and master's program. I also would like to thank Professor Mulder of Shell Corporation and Ernst Pabin for discussions, for fruitful discussions of the finding of my work. I would like to thank Sergey for agreeing to participate in the session of this Dissertation Council. Thank you very much. I'm very happy now. I would like to thank all the members of the Expert Assessment Center. Thank you for helping me with the documentation, with the administrative aspects of this defense. Thank you. Thank you, Mr. Ponomarenko. I would like to conclude by saying that this is the first dissertation being defended according to the new rules in the field of physics. Several dissertations have been defended in economics, in law, in the field of linguistics, philology, but this is the first one in physics. On this optimistic note, allow me to close the session.